Now we finally have enough information to solve a differential equation involving a delta function. So here's the differential equation we're going to work with, and we'll talk about what this means. So this is a damped harmonic oscillator of some sort, and remember that things other than just a mass on a spring will behave in this way in real life. So this applies to a lot of things. Here's the forcing function, and that's going to be a delta function. So what's going to happen is before time 5, there's no forcing function. At time 5, there's going to be a big impetus, and then after time 5, there's no forcing function. So this is like if something collided into your object. The object was fine, was behaving as usual. There was a collision, and then it's going to behave in a new way, but we don't touch the object after. It's just an instantaneous collision. That's what I was talking about in the first video with the billiard balls. And we'll put initial conditions. We'll put easy initial conditions. So that's like the object isn't moving at the beginning. Isn't moving and is starting from the position that we've called 0. Okay, so how are we going to solve this differential equation? We don't know how to do it normally. This isn't a function in our method of undetermined coefficients, certainly. So we need to take the Laplace transform of both sides. So what happens? We get 2. Remember, Laplace transform of y double prime. Okay, so first of all, let's let big Y of s be the Laplace transform of little y of t. And then the Laplace transform of y double prime is going to involve that formula with a bunch of subtractions. We decrease the power on s every time, and we start adding derivatives of little y, s times y of 0. Great. And then plus 2 times, and then here same formula, except there's one fewer term, big Y of s minus little y of 0. 3, Laplace transform is linear, so that makes that easy. And then equals, and this we just calculated, 5 is greater than 0, so Laplace transform of the delta function there is going to be e to the negative 5s. Okay, then we put in our initial values. Y of 0 is 0, y prime of 0 is 0, so all this ugly stuff goes away, and we're just left with 2s squared plus 2s plus 3, all times big Y of s equals e to the negative 5s. So big Y of s is e to the negative 5s over 2s squared plus 2s plus 3. So if we could just find the inverse Laplace transform of this function, then we'd have our little y of t. Okay, we're actually going to use a property to make this a little bit easier. So we're going to say let big H of s be 1 over 2s squared plus 2s plus 3, and then let little h of t be the inverse Laplace transform of big H of s. And then we're going to use those functions. So then y of t is going to be the inverse Laplace transform of big Y of s, which is the inverse Laplace transform of e to the negative 5s times h of s, big H of s. And then we're going to use a property from a previous video, maybe about a week ago, that says this inverse Laplace transform was the unit step function at 5 coming from there, times little h, so the inverse Laplace transform of big H, but shifted up to 5. We showed that property about a week ago. Okay, so now if I can find my little h, I can find my little y. So let's do that. First, we need to take big H and put it in a format that we can find in the table. So let's look. We have 1 over a quadratic in S. So this seems to be the closest. We have a constant over a quadratic. It's got an S term, so we can't use any of these. If it didn't have, if it only had s squared and not s, we could have used one of these. It has an s term, so we're going to need to complete the square to figure out what a is, and then we'll do a little bit more manipulation to it. Okay, so complete the square, and also we need the coefficient in front of s, down s squared, in the bottom has to be 1. So we're going to factor out a 2 from the bottom, which means we get a 1/2 out front. And then this is 1 over s squared plus s plus 3 over 2. And then we need to complete the square. So we got 1/2, 1 over s squared plus s. Half of 1 is 1/2. 1/2 squared is a quarter. So 1/4 completes the square. 3/2 is 6/4. So we need another 5/4, and now we haven't changed anything from there to there. Okay, now we need to match this format. We need, this thing is squared, that thing is also a thing squared. So we're going to write 1 over 2 times 1 over s plus 1/2 squared is the first part, and then this is root 5 over 2 squared is the second part. And we're getting pretty close. We now need, that's b squared, we need a b on top. So we need a root 5 over 2 on top. We can take a 1 over 2. So we just need we need to multiply top and bottom by root 5, basically. So we're going to be left with 1 over root 5 out here. We have an s plus 1/2 squared plus root 5 over 2 squared. Take a minute there. Convince yourself that this is the same as that stuff. Okay, now we're ready to take the inverse Laplace transform and get little h of t. So this thing is exactly this formula where a is negative 1/2, because we have a positive 1/2 here, and then b is root 5 over 2. So we can put that into our inverse, e to the at times sine of bt. And then we just have a constant of 1 over root 5 in the front. So this is e to the a we said was negative 1/2, negative t over 2, sine of b was root 5 over 2. So root 5 over 2 t. Okay, we found our little h of t, which means we can put it back into here to get our y of t. So y of t is going to be h of, we'll put in t minus 5 for t, and then we'll multiply by a unit step function. So 1 over root 5, u5 of t, e to the negative, this is now t minus 5 over 2, sine of root 5 over 2 times t minus 5. That's the solution to this differential equation up here. Let's think about if that makes sense. We've got a unit step function here. So, I need a different color. So what's happening? This was the graph of the direct delta function. Nothing happens until 5, right? The unit step function guarantees that. So our function is 0. This makes sense. We have a harmonic oscillator that's not moving. If you don't do anything to the spring mass system, it doesn't move. Okay, so we're not moving until we get hit with this direct delta function. Then after that, this is shifted, but this is going to be underdamped harmonic oscillation. Right? We have an e to the negative exponent, and then we have a sine or cosine function. So what's going to happen is we're going to hit it. I'm not sure how far up it'll go, but then we'll have a sine graph bounded by a decaying exponential. So this makes sense. We have a not moving object. We're hit with an impulse. It starts bouncing, but it's damped, so the bouncing gets smaller. So this solution, in fact, makes sense.